So now let's revisit what types of activation functions are more useful in neural networks. So between 1980s and almost even in the 90s, even in the early 2000s, there are two activation functions which are extremely popular. And by the way, activation functions are these functions that you have, the FIJs that you have, that each of the neuron computes, right? So the most popular in the pre-deep learning era of neural networks, right, have been the sigmoid activation unit and the TANH activation unit. We know what the sigmoid activation unit is, right? Because we use this in logistic regression, right? So let me explain the sigmoid activation unit. Let's assume I have an activation unit here. Let's call it Fij. Let's assume I get some inputs and some weights. So there is some weight 1, some weight 2, weight 3, weight 4, right? And I have some xi, x1, x2, x3, x4, etc. Right? So what do you get? So let's assume when you multiply wi xi, right? When you multiply wi xi and summate them, this is equivalent to w transpose xi. Sorry, this is equal to w transpose x, right? Where w is a vector of w1, w2, w3 and w4, and x is a vector of x1, x2, x3, x4, right? So the input that you get here, what goes into the network here is the weighted sum, right? You have x1 w1, x2 w2, x3 w3, x4 w4. You multiply and then you sum up all of them. That's what goes as the input to this. Okay, let's call that input as z. Let's call that input as z. So this is equal to, let's say, z, right? So what is the output here? This output here is Fij of z. And what is your Fij? If this is the sigmoid unit, let's represent the sigmoid unit with the sigma sign, right? So the sigmoid unit says the sigmoid of z is nothing but e power z by 1 plus e power z. Or you can also write it as 1 by 1 plus e power minus z. And if you recall our logistic regression, this is nothing but what we use in logistic regression, right? To squash the inputs, if you recall. So if you've forgotten, please go back and revisit the logistic regression chapter, right? This is exactly the sigmoid function that we used in logistic regression. And one of the most popular activation functions in the olden days, it's fun when I say that because 1980s and 90s is not really that old as compared to where we are today. Right? It's just a few decades ago. But still, this is pre-deep learning era. And deep learning only started in around 2006. The very first research paper came out in 2006, right? And it became truly popular only after 2012. So anything before 2012, I'll still refer to them as classical neural networks. So anything before that, I will call it as classical or old neural networks. Anything after this, I will call it as from the deep learning era, right? So sigmoid units are one of the most popular ones. Remember, what are the requirements of your activation function? It needs to be differentiable. And it should be easy to differentiate. It should be easy and fast to differentiate. Then you might wonder, why are we taking this complex function here? This doesn't sound like a straightforward thing. This looks fairly contrived. Of course, there are some reasonings for it from a probabilistic standpoint that we saw on why we have a unit like this. Remember, we discussed why we have the logistic regression. Why are we using the logistic function or the sigmoid function in logistic regression when we discuss logistic regression in detail in its own chapter? For now, from a pure differentiation perspective, sigmoid has some advantages. Okay, let's see. So if sigmoid of z is basically 1 by 1 plus e power minus z, and just to quickly recap, what is z here? Z is nothing but w transpose x. Okay, so if this is the structure you have, you multiply all of them, sum all of them, you get z, and this simply takes z as input and computes the sigma of z. So this is nothing but sigma of z, right? Some very interesting thing that you have here is, what is the derivative of sigma with respect to z? If you compute this derivative, what you'll get is very interesting. You will get sigma of z multiplied by 1 minus sigma of z as the derivative of the sigmoid function. The fun part here, the most important part here, the derivative of the sigmoid function is represented in terms of the sigmoid function itself. Right? Because if you implement a function called sigmoid z, you write some code, let's say. You write the code to compute 1 by 1 plus e power minus z. This function that you write here can be used during forward propagation. Because what do you do in forward propagation? You exactly do this. You multiply the inputs with the weights and you forward propagate it, right? You simply forward propagate it. So you can use this function in forward propagation as well as in computing derivatives. In computing derivatives. And computing derivatives is what you do during the backpropagation stage to update your weights. So the same function, because the derivative of sigmoid can be expressed in terms of sigmoid, right? This is very important. So the derivative of sigmoid is expressed in terms of sigmoid. So if you implement one sigmoid function, you can reuse it both for forward propagation as well as for computing derivatives as part of backward propagation. Again, this is not the only reason for it, but this makes sigmoid more interesting because it's the same function that I'm computing derivatives, which means it's the same function I'm using during forward propagation as well as during backward propagation for computing derivatives. Of course, there are more reasons on why sigmoid is good and things like that, right? So there is a very nice blog that I've referred to, right? This is a very nice blog. So this is how the sigmoid function looks like. We know this, right? It goes from minus infinity to plus infinity, and the minimum value is 0, the maximum value is 1. We saw this plot in a lot of detail in the logistic regression chapter. Where we discussed that this works as a squishing function or as a squashing function, right? So this is what sigmoid looks like, right? And there is a nice detailed explanation of how to compute the derivative of sigmoid. So if they're representing the derivative of sigmoid as a, the derivative of a with respect to z is a into 1 minus a. This is exactly what we wrote here. Derivative of sigmoid is sigmoid multiplied by 1 minus sigmoid, right? So they also derive all of these details. They apply chain rule for you. So if you really want to derive it on your own, please follow these steps. It's a very well written blog. I've given a reference link to this blog in the description section of this video. Now comes the interesting part. How does it look? This is very important. If the blue line is my sigmoid function, remember my sigmoid function has a minimum value of 0, maximum value of 1, right? And it goes from minus infinity to infinity. And it falls very, very sharply here, and it plateaus here, which means it keeps growing. If you look at this, if you look at your sigmoid, from somewhere from minus 4 to plus 4, right? From minus 4 to plus 4, it is growing. It's growing fairly well. But after that, its growth is very, very slow. Similarly, its fall is very, very slow. This line here, right? This pinkish line or this violet line here is the derivative of sigmoid. So this is basically the derivative of sigmoid with respect to x or z. Okay, if this is z, this is the derivative of sigmoid, and this is the sigmoid function itself. If you notice the derivative of sigmoid, the maximum value is here. And the derivative is also only significant between minus 4 and plus 4. After that, the derivative is extremely small, right? Because derivative basically says how fast is the sigmoid function changing. So the most important thing here is the derivative of sigmoid. The derivative of sigmoid is always less than, so if this is 0.2, it's always less than 0.3. It's actually small. It's always less than 1. And it's of course always greater than equal to 0. This is very, very important thing that we'll see why this is important in the next video. For now, just remember this shape, that if this is a sigmoid, my derivative of the sigmoid has a maximum value of less than 0.3, actually less than 1 for sure, because this is the plot, right? And 1 is here. And the derivative of the sigmoid is greater than equal to 0, but strictly less than 1. It never even reaches like 0.3. 0.3 I think is somewhere here. It never even reaches 0.3. But this is a very interesting function. Again, this problem that the derivative is this property of the sigmoid has some problems that we'll discuss in the next video. But sigmoid is also very popular because you can represent the derivative of sigmoid in terms of sigmoids themselves. And sigmoid also fits very nicely into the framework of logistic regression that people have been used to for many, many years, right? So sigmoid is one popular activation unit. There is another popular activation unit called the tan H function, right? The tan H function. So again, I've given you a reference link to another blog by the same person where they explain what tan H function is, right? So the tan H function is very, very similar to, so if you look at it, the tan H function is somewhat like your sigmoid function, and they both are related, right? And if this is your tan H function, tan H of z, right, is this, then the derivative of tan H with respect to z is 1 minus tan H square of z. Okay, so let me write it here. The derivative of tan H by z is equal to 1 minus tan H square of z. So even in this case, the derivative of tan H is represented in terms of tan H itself. It's 1 minus the square of the tan H, basically. Okay. So here there is more detailed derivation of the of this whole thing, and you can see the derivation applying chain rule, etc., etc. Lots of nice steps that somebody has put in here. The most important part for me is this plot. So if you look at it, the tan H function, unlike your sigmoid function, again, we looked at the tan H function when we were learning about logistic regression and optimization and linear regression. We also showed, so in our linear regression and optimization and logistic regression chapters, we also encountered the tan H function. The tan H function, remember, your sigmoid function lies, the minimum value is 0, the maximum value is 1, right? It's like this S curve between 0 and 1. Your tan H function is also an S-like curve, but the minimum value is -1 and the maximum value is 1. So instead of having the S value between 0 and 1, now we have the S value between -1 and 1. That's the primary difference. Number one, right? Number one is that it lies between -1 to +1. Instead of, it lies between -1 to +1 instead of 0 to 1. That's one of the big differences between tan H and sigmoid. But otherwise, if you look at this curve, it also looks like exactly the sigmoidal curve. Number one. Number two, if you look at the derivative, right, the derivative of tan H with respect to z, again, the minimum value of the derivative is 0. It lies again between 0 and 1. The maximum value, this purple line or the violet line here you see, is the derivative of the tan H function. And the maximum value it takes is 1. The minimum value it can take is 0. And if you notice, between -3 and +3, it has some reasonable value. But after +3 and after -3, the value of the derivative of tan H becomes very, very small here. Here it becomes very, very small. Right? After this, of course, there is some value here. It's also not very large, but its largest value is found at 0. And if you notice this shape, this is exactly like the derivative of the sigmoid unit that we saw. So if you look here, this is the derivative of the sigmoid. The fundamental difference here is, okay, let me draw it here, right? If this continues here, this is where you have your -1, right? Your tan H looks like this. It lies between -1 and +1, and it passes the origin at 0, right? And its derivative looks like this. Sorry, let me get a different color. Its derivative looks like this, right? This is your tan H. This is your derivative of tan H, right? And this is your sigmoid, and this is your derivative of sigmoid. If you look at this shape and this shape, they're very similar, except that this has a bigger bump. But the maximum value occurs at 0 itself, when x equals to 0. Except that even this looks like an S curve. The sigmoid looks like an S curve, and the tan H also looks like an S curve. Right? So because tan H is very, very related to sigmoid. even if you look at the formula, right? So classically or traditionally, TANH and sigmoid were the two most used activation functions because they're differentiable. That's very, very important. You can't have an activation function that is not differentiable. Then your whole backpropagation algorithm falls into the dustbin. It doesn't work. Okay, because chain rule of differentiation is the core concept that we're leveraging here. And they're easy to differentiate because you can represent both your sigmoid function in terms of itself, and you can also represent your tanh function, the derivative of the tanh function, in terms of itself. Right? There are more. So even though tanh and sigmoid are very, very popular in the 80s and 90s, the more popular activation functions right now are called ReLUs. Okay, we will understand about ReLUs in lot of detail and why do we need to come up with the concept of ReLUs in the next chapter, where we learn more modern techniques. So in this chapter, we are covering all the concepts in the pre-deep learning era. In the next chapter, we will cover all the concepts in the deep learning era of neural networks. But without understanding what came before, you won't understand what's happening now, right? So we will discuss other very, very important activation functions like ReLU. Similarly, we'll learn something called as Riki ReLU and things like that. We will learn this, and actually ReLU is the most popular activation function today, as of today. Again, deep learning is a very, very active area of research. As of 2018, ReLU is the most popular activation unit, but this may change anytime because people are always actively researching about better activation functions.